Thank you. All right. Let's move that on there. So yeah, thanks everyone for coming out. Hi there. It's great to be here. And I run infrastructure engineering at Verizon Labs. So this evening I'm going to be talking to you about the system we recently open source called Nelson. We've been working on it for about 18 months. And for us, it sort of handles all our orchestration and our entire runtime and deployment for one of our products, or a whole selection of products, actually, as it would turn out. So we've got about 30 minutes. I've got like 60 slides, so we'll try and go through them as quickly and efficiently as we can. So actually, just before we get into that, just quick, kind of give me a sense of who's here. How many people already run a scheduler? Greg, you can. I work with you. That's okay. So like 3 people. Okay, all right. So I'll give some background. All right. So problem statement. So from our perspective, so just a bit of background about what we're doing. We have about 500 engineering staff. And in the last 5 years ago, it took us about 2 weeks to get from code complete to deploy, which is obviously terrible. It was 5 years ago. And then about 4 years ago, I decided, well, this sucks. I'm going to redo it. And then I took that process and made it from 2 weeks to 20 minutes. And then, like all entitled developers, now you're like, 20 minutes? And it's just like a disaster, like how entitled people get about these things. So, anyway, so provisioning applications is still too damn slow. So we basically need to make it way faster. And runtime traffic control is like practically medieval. I don't want to hear about your canary ASG that you're going to put into your other one and then bleed in your machines. Like that's just is a complete nightmare. When machine is your unit of work, that's just simply not granular enough. So there was that, and coupling CI and CD, that you typically create these sort of monolithic systems, often around Jenkins, and often using immense amounts of Bash, which I'm sure many of you have written before arriving here today. And sort of the current market solutions are either limited or they don't do what exactly we were looking for. Kelsey Hightower is a nice solution that everybody wants to pass, provided it's written by them. Ironically, I guess that's kind of true for us in some senses, but hopefully in this talk I'll explain to you why that was. Most teams, at least teams that I've worked on in my last sort of 15 years of work, they're usually quite brittle. These systems usually don't scale well, and I don't mean that from like, that they're trying to reach Google kind of scale. I mean they don't scale well from a soft perspective. Humans find them difficult to interact with. They find them difficult to maintain. It's a shared responsibility, so it often ends up being a shared failure. From doing all these things, we learn a whole bunch of different things. First thing is, if you don't automate every part of your system, it's going to be an immense amount of debt. Not for. It's like yourself of a year later is going to thank you if you automate everything today. The other thing I absolutely love to talk about is that testing distributed systems is a complete fable. People are like, yeah, containers, like you can run them all locally and awesome. And then you see people and they're like, well, I've got this distributed system. And I've got like 300 services with and each of them's got a database, and I've only got like 16 gigs of RAM. And you kind of run into these things pretty often. And so just testing distributed systems is really, 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 really hard. Not least to mention the fact that you get emergent properties in distributed systems that are simply not testable by you because you don't know them a priori until you've seen them in production, millions of requests. So likewise, uniformity. Uniformity has been like this huge, huge thing. That if you can make things uniform across your system, regardless of whether or not it's a system job or a task or whatever it happens to be, this is kind of like accommodate the 80% best you can, or 80 to 90% ideally. And depending on the scale of your organization, the more engineers you have, this will cover larger and larger portion of the services and systems that you actually build. How unfortunately that the beautiful snowflakes are somewhat inevitable, and you kind of have to deal with them. So I'll be talking a little bit later about how we ended up dealing with those snowflakes because, yes, I wish they didn't exist, but they do. Also automated lifecycle management. How many people here run on AWS or Google Cloud or Azure? Or, okay, most people, right? So presumably at some point you have given all your money to those people, and because you leaked drives or you forgot that, hey, EBS doesn't clean up after itself, or any one of those kind of things. And then you get the bill and you're like, wow, we spent X last month. So these kind of things, you need to clean up everything. And it should not be, if you're shipping more applications, if you're doing CI/CD, you absolutely have to be cleaning up everything. If we were like, okay, 18 months ago, we were like, we're going to build a new system for this, and we absolutely want to achieve a few things. So the first thing we want to achieve is we want to use the absolute minimal powerful components. And so we have this sort of internal mantra, which is that constraints liberate and liberties constrain. And it's sort of this kind of interesting thing that if you decide on a set of constraints, the fact that you don't have choice actually liberates you and you can think about other things. Because why bother? You have these constraints, so it actually frees your mind to think about other things. And so this is kind of the way we think about distributed systems. By and large, we do a lot of functional programming, and we kind of use this sort of composition, design for composition, as kind of a driving force about when we design distributed systems, because it turns out what works in the small also works in the large, if you kind of adopt this kind of mentality. So yeah, so I want Unix philosophy. System elements that do just one thing. Build system that is an awesome build system. Deployment system that's an awesome deployment system. I want a monitoring system that just does monitoring. And I don't want to couple these things. So this was sort of underpinned by a desire to kind of reduce platform complexity. Our previous system, the one that was running at about 20 minutes, was this kind of monolithic system. I like to talk about it in the third person, like someone else wrote it, but really it was my mess. So kind of it's always kind of amusing to think about that. So yeah, but from a platform complexity perspective, what we realized was that by having this, like these developers kind of have to go in and like make some changes to allow for their systems to work. That there wasn't really a great deal of responsibility because it was just a shared system. And so instead, by adopting a break it, you bought it, it's your code, you're on call for it. It's sort of driven up developer responsibility. And last but not least, we decided that decentralizing process gatekeepers, we literally got rid of the build team. There is no build team. You are the build team. And for example, and so no filing tickets for deployments. Once you commit to master, it's deploying. No configuration management. No janky chef scripts that you have to go in and adjust because you need some new thing. And you're not sure if you're going to break someone else's deployment because it's runtime Ruby evaluation, blah blah. So sorry for anyone who uses those things. So we sort of kind of got on this train of yes, immutable everything. In addition, we realized maybe 3 years ago that anything that's not checked in is a complete nightmare. It's a liability for you at a later date. So we actually check in everything. Building, deployment, alerting, everything is checked in. Everything is revisioned. There's not a single thing that we do that is not revisioned. That may seem obvious, but I know that many companies don't operate like that, particularly for things where it's clicky dashboards and so on, or AWS console, probably for a lot of people, or Google Cloud Console, or whatever it happens to be. So our goal was to reduce deployment time to 2 minutes or less. So I want to be able to iterate on the production cluster. I don't want to be kind of waiting around for these things. Now, depending on your language that you're building in, your sort of mileage may vary with the build system, but I want all the builds to sort of the outlier execute in less than 10 minutes. For large projects, that's kind of obviously 10 minutes is quite a long time, but still pretty fast compared to where we were. But in the main case, I want things to be deployed in a couple of minutes. And I want to be able to support multi-DC topologies. So in our case, we want redundancy over multiple clouds or multiple data centers. It doesn't really matter, but I want to be at multiple discrete targets that I want to be able to deploy to in a redundant fashion. So yes, and just the last two, encrypt all the things. It just blows my mind that people aren't encrypting everything these days. We want encryption on the wire, want transparent encryption so that the applications don't have to deal with that. This is typically by the way, who here understands TLS? We've got a tentative one person who understands it, but everybody uses it. This is a classic thing with SSL and TLS. Everybody wants to use it because it's the industry standard, but basically nobody understands it. So we want to provide this as a service for everybody, so it just happens. You make a request, it's encrypted, period. And we'll be talking a little bit about that later, because that's sort of one of the most interesting parts. Automatic credential management is also this big thing, and secure introduction, that's also kind of fascinating. So I'll talk about that in detail when we get to the get to that part. So we decided, yes, we are going to build this thing, and we will build it better. And so we decided to build it with these tools. So Console, Nomad, Envoy, Vault, and the one on the right is Nelson, which it came to be. So first thing we're going to talk about is Nomad. So for those who don't know, Nomad is a resource scheduler, or resource manager and scheduler. So in broad strokes, you can think about it such that instead of having an application foo that you put onto a particular server and they say that server is for this application, you just treat your servers like cattle. And instead of saying I've got this server with 10 gigs of RAM or whatever it happens to be, you say, okay, I've got a data center, and that data center has 10 or 8 terabytes of RAM, and it has X number of cores, and I just treat it as a sort of homogeneous thing that I can deploy to. So several competitors in the space: Kubernetes, Mesos. We also are a long-time runner of Mesos. If anyone's interested in sort of Mesos versus Nomad, sort of the kind of thing, I can talk to you about that. Sort of different, basically the bar to entry is different for all these things, and it depends on your particular org and what you're trying to achieve and how much engineering resources you want to invest over the sort of next, 2 to 5 years. But so for Nomad specifically, these schedulers are sort of typically used at larger scale. If you're a smaller shop, it sort of makes less sense because of the operational complexity involved. But if you are at that kind of point, then it makes an immense amount of sense, simply because it's a better deployment model. We'll be talking about that a little bit later. Nomad is like crazy fast, like ridiculously fast. So it's been benchmarked in the field at doing 24,000 container deploys a second, which is ridiculous, frankly. The Citadel in the UK, they're a high-frequency trading company that they're basically trying to evaluate models for quants to look at. So frequency of deployment across multiple clouds is a really big deal for them. In our case, frequency is not 22,000 container deploys a second, unsurprisingly. But nonetheless, it's a nice feature, and we do actually care about the time to reschedule and these kind of things. So there is a degree of frequency, we care about it a little bit, but nowhere near as much as those guys. So just as a sort of interesting side note, Nomad is integrated with Vault. So Vault is another product from Hashicorp, and there's a sort of very interesting problem that happens with schedulers. So if I'm launching a container, or any kind of job, containerized or not, let's just for argument's sake say it's containerized, well then you've got kind of an interesting problem because you've launched another process and that thing needs secrets. But how do you know that that's the thing that you actually launched? And so there's a sort of interesting relationship about like the only agent in the system that knows if it actually launched it is the scheduler. So anything else you do is a crazy hack, basically. Like because you have what's called the first key problem or secure introduction problem. And so this problem is kind of a well-known problem that sort of resolves around the fact that I can't identify you. I can't issue credentials to you before I've identified you, but I can identify you with you having some credential with which to identify yourself with. So it's this kind of like cyclic problem, and so you have to make a degree of trade-offs. And so Nomad handles this by saying, yes, we trust the scheduler, so if you're so inclined, you can secure boot your machines and then kind of have security all the way up so that anything that you launch, you trust the scheduler launches a container, and then it's integrated with Vault, so it does this one-time handoff for every, you can read about this in the documentation, they call it the cubbyhole method, but it basically has a one-time token that when it launches a container, it sort of launches it with this thing, that credential can only be used by that specific container, and then that specific thing is then used to talk to Nomad, which talks to Vault, and then it kind of negotiates the secure introduction from there. So in short, all of your containers have this unique token, and that unique token is unique to that container, and you get unique credentials which are time-bound for that container. So in the event you get compromised, the only thing you've lost is whatever was issued to that container. So you can just turn it off and burn it, and then nobody cares. And Vault itself can generate credentials from any backend. So like in our case, like we can dynamically generate credentials for, say, Cassandra, and the credentials themselves are completely throwaway because they're generated based on a policy. So you've got dynamic containers that are like ephemeral, with credentials that are ephemeral, with certificates that are ephemeral. You kind of get where that's going. So it's pretty nice. And just last note for any of the scheduling geeks, it's a monolithic scheduler, not a two-phase scheduler like Mesos. So yeah, it basically means it's doing both the resource management and the actual scheduling. So it's not as pluggable, it's not as customizable as say something like Mesos, but obviously it works right out of the box. When instead of Mesos, you need to write your own scheduler, which is obviously a lot of work. So the second component we decided to use was Envoy. I'm just curious, who's heard of Envoy? Can't say that, JD. Anyway, so yeah, okay, a few people, that's good. So it's hot right now, obviously, so I guess we just have velocity conf. People have been listening to Matt Klein's talks, that's all awesome. So Envoy is a super fast L4, L7 proxy solution, and it's kind of filling a neat gap that is frankly sorely missing. So for a lot of us, for these kind of requirements, might use, say, Nginx or something like that. And sort of Envoy is kind of fixing some serious problems that exist in these other solutions. Now, not that they are bad solutions. It's just that from an operational perspective, like in a more dynamic world, I can't make assumptions about my upstreams, for example. So in this case of like Nginx doesn't re-resolve DNS. So it's like the IPs that it resolves when it's booted, they're the IPs that you have to use in perpetuity. And obviously there are hacks that you can now put in to like try and negate that, but it's not a nice solution. It's not doing like async DNS off the bat, and okay, they have that in their paid product, but I kind of want that by default. I want a sane default that's going to work in an environment where I'm moving workloads around the cluster to sort of satisfy my other demands. So Envoy does this kind of thing. And it was open sourced at the end of last year, and it's kind of blossomed. Google, IBM, there are more people working on it at Google now than there are at Lyft. So it's you see this in the channel every day if you're interested in joining. And yeah, it's just a super fun project, and we've been using it for quite a while. So the general idea for us is to make applications dumb, and we want to invest in a single element of routing infrastructure. So for example, even if you try really, 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 really hard to have a homogeneous infrastructure where everybody is programming in a single language, and I don't care if that's Go or Scala or whatever it happens to be, you will end up at some point in your company's lifetime of having multiple languages. And so being vertically integrated is super hard. Having libraries that you have the library for monitoring or the library for routing, and it's like then the website people come along and they're like, yeah, we really wish we could use Node.js because we don't know C. And you get these kind of conversations, and that's completely reasonable because that's their skill. So we kind of adopt the approach that, in fact, actually we want to empower them to do the thing that they're good at, and we will just make everything that we need work around them. And so, in that case, regardless of whether or not you're Node or Scala or Go or whatever it is, if you make a request, it gets transparent encryption. The outbound request goes to Envoy, and then Envoy handles everything else from there: retries, circuit breaking, encryption. It turns out that this is super nice because then suddenly you don't have applications having to figure out, like in the case of the JVM, I know there are probably a bunch of ops people here. Has anyone tried to configure a JVM key store? It's like a complete disaster. So, yeah, so, this is kind of really nice. And so, if you think about the conversation we were just having about dynamic containers with dynamic certificates with this Envoy, then you could be like, well, I've got dynamic certificates issued to an Envoy that's going to make a dynamic request based on, so it can actually propagate these kind of things for you so that when I make another request, someone else can identify me via my certificate, which was custom made for this container based on my certificate. So you get this sort of very nice kind of model kind of emerging out of this stuff. Now, if you decide that you don't want to do a DNS-based approach, you need something more sophisticated. Envoy has this sort of pluggable set of APIs where you can actually provide a system, to give it the answers that it needs. So, for example, if I've got the name, like a logical name, like account service, and I need to know where that thing is, it can reach out to an API and then turn that name into IPs. It has a set of APIs. I won't go into the other ones. The other ones are sort of more complicated to do more advanced stuff. Dynamic routing, dynamically choosing hosts, dynamically choosing paths, dynamically choosing all these different things, dynamically binding to different ports, all sorts of crazy stuff that you can do with those APIs. And indeed, we have a whole subsystem that deals with this. Because in our case, we do want that kind of advanced functionality. So these are our building blocks. I'm not going to talk about console. I guess probably most people are familiar with that. I'm not going to talk about Vault because I could probably fill another talk with those kind of things. So. Anyway, so Nelson, the first question I get is probably like, I get, why has it got a stupid name? And then I get this a lot in America. I guess in the UK, like Admiral Nelson's sort of this very historic figure. There's a huge statue of him in London, and I guess most people know who he is. Turns out that's not the case over here, so I have to explain this every time. So Nelson was an admiral in the Royal Navy. He has this really nice quote, which is desperate affairs require desperate remedies, which, when your pager duty goes off at 2 a.m., you're like, yeah, there are definitely desperate remedies. So a bit of an overview about what we've been building, and just to give you an idea of kind of what we're going to be talking about. So Nelson is essentially completely driven around GitHub. We use GitHub internally, enterprise, but it works with .com. It's all the same APIs. You can choose whatever CI build system you want. It's completely up to you. You get state-of-the-art runtime routing via Envoy, although we are specifically not prescriptive about that. If you did decide that you wanted to do, Nginx and Lua, you could do that if you wanted to. We'll talk a little bit about that later. Because we're using Nomad, we get secure introduction. We integrate with Nomad, but we can target any data center running a scheduler. If anyone's interested in the implementation details, you can easily basically add another scheduler. For a while, we had this sort of mixed mode thing where we had both Mesos and Nomad. We ended up taking out the Mesos one simply because we weren't really using it that much in the end. And we get integrated alert definitions for Prometheus. We validate those things. Again, it's pluggable. You can implement your own if you want. So from a process perspective, this is kind of generally how it works. You put your pull request up with your awesome codes, and then one of your esteemed colleagues will look at it and obviously merge it because it's so good. And then GitHub will then say, hey, Travis, build this. Travis goes and builds it. By the way, we run Travis internally, but let's just say it's .org. It doesn't really matter. Travis will build it, and then it will publish the container to what we call staging registry. Now, the staging registry, it's just implementation detail. It could be the same registry as your data center, but just from a workflow perspective, it's like logically different. And Travis, once it's done, it will be like, hey, GitHub, I'm done. And then GitHub sort of then, we use webhooks via the GitHub applications. GitHub then notifies Nelson and says, hey, new release, do your worst. And then Nelson looks at the release and kind of figures out, is this something I should deploy? And in the event it is, it starts its whole workflow process about actually slinging this application out into the relevant data centers. And we talked earlier about lifecycle. So it turns out that this is sort of one of the hardest and sort of most interesting things about running large-scale systems. And so we have this kind of interesting state graph. So obviously pending, obviously it's going to be doing it. And then deploying is the actual deploying, and then it goes into this interesting warming state. So console has this kind of notion of health check. And you can say ahead of time that this application is healthy once X condition is met. And so we've realized over time that there's this kind of interesting thing that even though the ports are active, it might be that the application is still warming up. And so the application, we delegate to the user and say, you know what, you can tell us when you're ready to receive traffic. All the while your health checks are not passing, you're not going to be in the routing, you're not going to be available for routing, you're still going to be warming up. And so we don't put you in the routing graph, and we'll be talking about the routing graph in a minute. And then you move into the ready state, which is of course the typical state, and then we have this sort of interesting workflow for stopping other people using things. So in the case where you had like a 1.1 of your system, and then later, some time passes and you want, I'm going to do a 2.0 of my service, whatever. You might decide that I really need people to stop using the 1.1 version because it's legacy. You can deprecate your system, and then anyone who was using it will they will get a fat warning which says, hey, this thing is deprecated. You need to upgrade. And so you kind of flip that around so that most of the time what you find is people do these things and then they're like, oh, sorry, did I break you? Or these kind of things happen in like large teams simply because you don't, the teams are so large, they're not really too sure who's using their API. Like you provided an API and kind of like it's been so successful, you didn't know who was using it. So by doing this, we kind of codify all the things that you might want to do in the system. In the more common case, your application becomes garbage and it gets garbage collected. So obviously that's an interesting thing, so let's talk about it. How do we do garbage collection? How do we decide whether or not something is going to be collected? Should we kill it? Should we keep it? And what we realized was that absolutely every application is running on borrowed time. Doesn't matter whether it's today or tomorrow or next year. There will be a time where you do not need that application. Maybe you've got a new version. Maybe you've just simply UL'd it. But there will be a time where it is not needed. And this was kind of a really key insight, and we realized over time that simply by bumping the expiry, we can kind of just have these things just naturally fade out, and then they get garbage collected. By the system will come off and just turn them off because they're not needed anymore, based on the policy. And we'll talk about the policies in just a second, because I know some people are sort of frowning, being like, that sounds weird. So we would just mark it for garbage, and then eventually we basically invert the workflow that we use to deploy it, and then we just tear everything down, clean up all the vault policies, clean up everything, all we created, we destroy. So one of the interesting kind of policies we have is this kind of graph pruning, which kind of trims your distributed system like a bonsai tree. And the thing is, in the case where I had this sort of small system, so in the case I got service F, like version 1.2, and I said, hey, I'm going to do 1.3 of that service, and I'm going to get rid of my dependency on G. Nelson will come along and be like, hey, nobody else is using G, then we don't need it. What's the point of running it if nobody is using it? And so Nelson is sort of logically aware, and if anyone's interested, I can show you how it knows this, but Nelson is aware of all the dependencies your application have, like all of them. So whether or not it's a database, whether or not it's another service, whether or not it's an external vendor, it knows about everything that you depend on, so it can make these logical decisions, and we treat the entire topography as a graph, and we are like actively maintaining and actively updating the graph. So this is sort of a super powerful feature because it turns out most of the time the developers are like, ship my code all the time, and they never think about like this evolution of it. So it's indeed they don't go back and be like, okay, let me do the tedious thing and clean up all my other applications. So I think this is kind of unique. Not many systems are doing this, regardless of what schedule you're running on. I haven't seen anything else that's doing this. We have other policies, for example, like keep the last two major revs, and this is typically used for like data science modeling, where they objectively want to quantify like, data science model X versus Y. Did I actually make it better or did I make it worse? So you see these kind of things. Other typical things, usually in jobbing, sometimes in services, keep the last 2 feature versions. And these are pluggable policies. These are just like 3 examples of the things that Nelson supports. But you can kind of quickly see by having this policy-based lifetime, you don't need to like worry about cleanup. You just stop thinking about it in that way. And you just be like, let the system handle it. It knows what your dependencies are. It's just going to clean it up when it's not needed. So namespaces. This is sort of a really interesting concept. We're going to get onto the meaty bit about routing. So broadly speaking, you can kind of consider the system like this. We have many machines. Nomad sits on top there, which is our scheduler. And then we kind of apply these virtual namespaces. And it turns out that these are completely virtual. Like there's no real, there's nothing actually there. It's an entirely virtual concept. It's completely synthetic. And so you can kind of imagine these sort of both horizontally as like, in the classic example, like dev QA prod. These names are completely arbitrary. You could choose whatever you wanted to. We don't really care. You can actually build trees of these namespaces. So you can have a root namespace, which in this case we'll call QA. Maybe you want like a QA unstable, and maybe I'll add my own namespace, QA staging Tim. Now, why is this all useful? It sounds kind of weird, right? So it's weird because I can deploy my application, but typically what I want is I'm making modification to my service, but I don't want to impact anyone else. I don't want anyone else to see that thing. I just want to deploy it because I need to know if it works before I'm able, like, did I even do the right thing? And so typically what you want is I want like the stable world with my one change. But it turns out everybody else also wants their stable world just with their one change. And if you have that in a compound environment, the whole thing is completely unstable. I'm sure everybody's worked in a place where they're like, yeah, dev is a disaster. Nobody uses dev because it never works. And like all of these kind of things. And everybody knows that this happens, but yet we never try to do anything better about it. So this is kind of our way of trying to do something better about it. And so by having these arbitrary namespaces, and because they're completely virtual, they're essentially just a database entry, we can have as many as we like. And so when I actually come to resolve dependencies, it will first look in my namespace, which in this case is QA staging Tim, and then it will look in staging, and then it will look in QA. And so this kind of has the net effect of being able to like look at this aggregate view of the way that I actually resolve my dependencies. So obviously we need to talk about discovery and routing now. So these things are closely related, but it really is important to understand that they are different. Discovery is sort of the act of simply taking like this logical service name like accounts or like foo or whatever you want to call it, whatever the logical name of your system is, and tell you the fully qualified name that it's currently running as, the current stack it actually resolves to. Routing, on the other hand, is kind of the sort of moving traffic around the system. How do I actually send requests from various systems? How do I get in between those intercommunicating systems? So in our case, we have this discovery protocol. We call this the Lighthouse protocol, and we write it out to console KV for every stack. So a stack for us is like a physical deployment of a logical entity. So for example, if I've got the foo service logically, I might have the foo 1.0 service like as a unit, like a sort of a logical implementation, and then I'll have like foo 1.1.1 with some hash, and that thing is like that's a physical thing that actually runs my foo service. So in the case I had like, let's say I just redeployed that same thing with a different configuration, it would have a different stack. Oh, that's a little bit abstract. We'll come back to that if anybody is interested. It's just implementation detail, but because these application dependencies are declared a priori, Nelson is able to make this routing graph. And so because it knows all of the things that you route to, you simply can't route to anything that Nelson doesn't know about because it won't write out the data. It won't write out the routing protocol to the runtime. So this has a really, really nice side effect where security rub their hands together and are like, awesome, we can audit everything because all they need to do is just look at the protocol and they'll be like, yeah, it's not defined, you can't route to it because you don't get credentials because it's integrated with Vault. So, and because of the certificate stuff we were talking about, you just can't call the other people because you don't have a certificate, because it wasn't generated for you because we have trust in the scheduler. And so this is just awesome for auditing and security. From a language implementation perspective, you only need to consume the protocol. We typically try and incentivize that. Yeah, we'll talk about that in a second. So the routing tier itself is completely non-prescriptive. We don't care. Obviously, it's much better if you use Envoy. Some of the things we're talking about can really only be done with Envoy versus some of the other things that are available in the market. Not to say it couldn't be done, but it would be, you'd end up writing a lot of other stuff. So we are primarily providing a control plane which describes the routable actions, and it's minor application change essentially. The only thing you need to do is be able to resolve these namespaces and read the Lighthouse protocol. So typically, there's kind of an additional thing you might want to do, which is if I've got system A, which calls system B, which calls system C, well, I need to propagate information, request to request. And typically speaking, this is a complete pain because it is actually an application change. I wish I had a good story for that, but you need the developers in your teams to actually do that. And we've typically tried to incentivize that with tracing to get the context propagation we need. So if you do this one thing for us, we're going to give you this really awesome insight, which is to see the latency in your distributed system along all the call chain. And so, that's sort of, it's a tough one, but that's the only thing you can really do. And sort of really interesting point that Nelson is able to actually model the traffic shifts as time versus policy curves. So you can actually choose the curve you want. So you could say, like, I don't know, like the default is a linear bleed or linear traffic shift, and it will actually start shifting the traffic linearly, one to the other from service from 1.1.1 to 1.1.2. Let's say you just did a patch version, and it will actually shift the traffic from one to the other. And you can actually say, okay, let's say I said it was over 4 hours. I can actually go watch my graphs. Okay, how is it doing? Oh, it's doing poorly. Push it back, and Nelson will just flip the graph around the other way and start to push traffic back. So there's no stopping. You don't just be like stop the traffic shift, because that causes like other runtime issues. So instead, we just push the traffic back to production, and then we'll go and look at the metrics and see exactly what happened. Likewise, you use power curve, logistical curve, atomic shift, whatever sort of best suits your application. So how does this actually play out? So this is from a blog post I wrote. It's already public, so So one way is that you can embed Envoy in your application container and just expose that. All of these have different trade-offs, different security trade-offs, different performance trade-offs, different overhead trade-offs, all the different things. So none of these things are a panacea. But in this case, comes in, terminated by Envoy. Envoy then passes a plain text request inside the container to the application. Application does whatever application logic it was going to do. And then if it needs to make another request out, it does so using our Lighthouse protocol, calls out to Envoy, and then Envoy transparently routes that to wherever it needs to go on the cluster. So the real problem, which I haven't mentioned here on the slide, is that what you typically find is in a scheduler, ports are finite. If most of our applications are sort of running upwards of 100 applications, each node. So you end up in a sort of system where the ports themselves, not everybody can bind to port 8080, obviously. So you have to do port remapping. And when you do that, each instance of my application, every single one, if I've got 100 instances of a given application, well, they're going to be on 100 different ports, more than likely. And so you kind of run into this very interesting thing. So Envoy is aware of all these port changes based on the APIs. In this case, these are the 3 APIs we implement right now on another subsystem, which we haven't open sourced yet, but you can implement it to your heart's content to integrate with whatever discovery system you want. So by doing this, we resolve those logical names to the IP port combinations wherever they happen to currently reside on the scheduler. And the really nice thing about this, as it would happen, would be that because all these things are known to console, if they get moved by the scheduler, well, Nomad moves it to another node because of bin packing, whatever, and then it moves to the other node, and then console says, oh yeah, it's over here now. And so the node that it had in its service catalog moves into the unhealthy state because that thing is not available anymore, and because Envoy is basically polling this sort of subsystem to get this information which is integrated with console, we don't take unhealthy nodes. So you get this kind of very nice, transparent, like anything that's unhealthy, we just don't route to it. And it's sort of dynamically coming out of the routing plane. Just if the scheduler moves your service, great, we don't route to it. And so, obviously one instance of your service should have many hundreds of instances for any real production service. And so another mode you could run this if you want like Kubernetes style like pod. Nomad calls this a task group, but it's called sort of sidecar. They call it a sidecar pattern, but it's a task group, which means that multiple containers get co-located on the same node, and you could also set it up like this if you wanted that kind of deployment. Likewise, you could also do it so that you were running it like a monolithic load balancer system on the host. I guess a little bit like Kubernetes does with kubeproxy. So there are multiple ways to run this stuff, and it's completely not prescriptive. You can choose whichever way you want to do it and choose your trade-offs for your company and do whatever you want to do. But sort of from Nelson's perspective, you just consume the protocol. It's going to clean up your system, and yeah. Obviously, it wasn't all plain sailing. I'm not going to stand here and say, yep, we just slammed it out and there's no problems. Frankly, this is a non-trivial level of investment. It's taken us 18 months to build this. We're a team of 4 people. So there are a lot of details, a serious lot of details. Obviously, we have pretty tight integration with the Hashi stack, depending on your sort of view of the world. This is either a pro or a con. The system itself is pretty pluggable, so if you were interested in doing something else, you could just implement the free algebra for that thing, and then you would be able to work with that within Nelson as well. But right now, it's sort of mainly a Hashi stack. Containerizing legacy applications can definitely be kind of interesting. They're typically not designed to work in like cloud-native way. They don't have monitoring. They're used to having logs in files, like all this kind of stuff. So that's like a general kind of gripe, but it's definitely a real problem. And migration, in our case, our sort of new world and our old world co-locate together. So migrating to the new world is super easy. But if you were trying to, say, for example, move from a secure private data center into the cloud, this would be really, really difficult if we had to do that. But in our case, we were co-located with the new world already, so we were able to do it. I will just say that the only reason it would be hard is not because of the networking or any of the technical implementation details. It's because you're coming along and saying, I've got this big gnarly system that I don't really know how it works, and I'm going to apply a lot of rigor to it. And that's something that most organizations typically don't receive that well because someone actually has to figure out, okay, what systems depend on what systems? And most companies that I've seen, once you get past the sort of 100, 200 services mark, they actually don't know. You can't find one person who can tell you what the service graph looks like. You'd be like, draw the service graph. And they might be able to tell you about their subsystem or a small part of their world, but typically speaking, you get to the point where one person can't tell you about all the different things because you end up with hundreds of logical services with thousands of deployments, and those thousands of deployments have many thousands of containers. It doesn't really make sense. So having this kind of rigor where you have a system that is that system, the design of the system is codified, that's really, really powerful. I guess also small organizations, this is not a lightweight solution, I wouldn't say. So if you have a small engineering team and you're 5 people, probably this isn't the solution for you because this is also solving a lot of soft problems, which is that it's codifying and adding rigor to the fact that it's sort of trying to abate Conway's law to a degree. Small organizations probably better served by existing solutions. Future work, what were we going to do if we, as we continue to work on it? I'm hoping that we can open source our console Envoy integration. There are some internal implementation details we need before we do that. The other thing we have internally, which is a cost analysis subsystem. So when you're running on a scheduler, you kind of end up in these interesting kind of situation where you're like, well, I know what the CapEx and the OpEx is for my particular node, but I've got an application which is using a portion of a node for a given amount of time. It becomes difficult to reason about cost. So we actually have a system which looks at all this and then basically makes an assessment like what is the per hour cost to run application Y? And you can make a business decision about, do we really need to run application Y? Because it's using 1,000 cores. So you can our goal is to try and objectively reason about things and provide tools that allow us to do that. I guess future work, I'm sort of punting on it a little bit, but it would be good to make Nelson easier to extend for third parties. If you're a functional programmer and you like free monads and free algebras, it's awesome. But for people who are not into functional programming and algebraic programming, it's perhaps, it's going to be a little harder. So we might provide an external DSL for workflows. We might externalize our policy algebra. These are probably the lower hanging fruit. We might make a plugin system. It's a possibility, but we'd have to think about what we will. But inevitably, we will probably try and do that. I guess more than anything, we want to listen to community feedback and sort of figure out what people want and is this useful and is it useful for other people? I mean, even if people just get inspired by some of the ideas, I'm stoked with that. So a quick summary. Nelson's providing you a sort of fully automated, lights out, no manual housekeeping, no manual crutches, and it takes a pretty hard line about the way you should run your application. No SSH access, all logs being moved out of the thing, all monitoring. If that's something that's appeal, it's awesome for that. You can choose whatever CI setup best fits your team. You can secure deployments, transparent MTLS, rotating credentials, vault policy management, and as I keep saying, it adds rigor to your Death Star. With that, I'd just like to say thank you very much for listening. I appreciate I'm British and I talk very fast, so if anyone's got any questions, I will happily answer them. Not a single question, it's like crickets. Yes, thank you. So packaging formats in sense of? Oh, yeah, yeah. So we just run it as a Docker container. We publish a Docker container on like hub.docker.io. So it's actually built in Scala, so it runs on the JVM. So we could build a fat jar and publish that if you're interested. But if you didn't want Docker, yeah, we could absolutely publish that. Nobody asked for anything other than Docker right now, so we run it. We publish Docker container for it. So, but if you would like something else, we can absolutely do that. Just for it to deploy Nelson. Ah. Oh. Sorry. So question was, can it support other things other than deploying Docker containers? The answer is that no, today it doesn't, primarily because that was an easier packaging mechanism for us. That was what we wanted to do. There are some issues with networking and stuff. I guess there's nothing stopping you having an alternative workflow. So Nelson has this concept of workflows, and it's just like you implement a workflow, and it will basically, that's the thing that defines how it will talk to the scheduler. So you could absolutely, let's say, for example, you wanted to like raw exec or do some other kind of like lower level thing without containers. You could absolutely do that. You just need to provide another workflow, and then it would just work. I mean, you'd have to write some code to do that, but yeah, there's nothing precluding that. Does that answer your question? Okay. That's right, and that's kind of one of the main reasons we decided not to do that, primarily because, so there's this other interesting thing, like operationally we want to prioritize robustness of the cluster. Like for example, we have this system that uses like it's extremely bursty and it expands its workload itself. So we work around the beautiful snowflakes problem by basically saying, you know what, everybody's a container, and if you need something more powerful and you really want to reach into those power tools, well, you're just a job that deploys jobs. And so this is a very interesting thing that comes out of this. So we have this one particular system I'm thinking of. So it spins up. So we launch it, and then it just goes off and makes like thousands of containers. And so that thing is then basically like a mini scheduler on the scheduler. And so in that case, you could absolutely do something like that, but it becomes problematic because if that thing goes rogue and it's got thousands of containers, it could like host the cluster if you don't have containerization. Because like in this case, like we actually see this where if the CPU runs away, like in his process or his sort of child processes, like we don't care. The only thing he does is strangle his own process because it's in a C group. So, from an operational reliability perspective, I'd probably be really reluctant to run this kind of conversion infrastructure without some kind of containerization, or at least at the C grouping. Like, if you could do maybe systemd spawn or something like that if you didn't want to use Docker. In a shared environment, you really want some constraints on what they can and can't do, some isolation, or soft isolation, because containers aren't isolated. The great debate. So the question was, do you run data stores on the scheduler? And no, we do not. So running persistent systems, in my humble opinion, after many years of trying to do it, is a complete and utter disaster. We ran Kafka on Mesos and Cassandra on Mesos and stuff for years, actually. We tried to make it work. And there are so many details. Like once you get to a certain scale, if you've got like terabytes of data or petabytes of data in your store, if the scheduler's like, hey, bin packing, I'm going to move that Cassandra node, and then you're like, and Cassandra's like, hold on a second, I'm syncing, and then it takes like 2 days to sync because you've got like terabytes of data, it's just a disaster. So these kind of subtle details, what you end up doing is you end up partitioning your cluster, basically, which is static partitioning. So it's like, well, why would I go to the hassle of doing that when I can just run it statically and just treat that? And so we actually have this special case in Nelson where you can, it's called a manual deployment, and you can inform Nelson about something that was not deployed with Nelson, and Nelson will then treat it as part of the routing graph, but it knows that it's kind of this special case that it can't clean it up. So it can remove it from its system so to forget about it, but it can't actually clean it up. And so this is basically how we treat databases. Yeah. Yes. Yep. Yeah, seems to work, I guess. Yeah, we do use that. So in Nelson, actually, you can, if you want to, there are basically two types of, we have this concept of unit. We kind of ripped off the name from systemd because it's such a good name. And so from a unit perspective, as a unit, you can expose ports, or you can decide I want to execute on a schedule, or I want to be a one-shot job, or I want to execute like monthly, or whatever it is. And so we provide a few convenience things. I wasn't planning on doing a demo, but I kind of really want to do a demo, but I probably shouldn't. The demo gods would frown on me. So Yeah. So you can declare a periodic schedule, and then Nelson's like, oh, you're a periodic job. Okay, no biggie. And then when it gets to launching it to the scheduler, it just sets all the periodic bits and bobs that are needed, and it launches the job. And then from a Nelson's perspective, because the actual running and the logical entity of that application are separate, we can ask the scheduler any time, do not run that thing. So when it gets cleaned up, if it's actually running or not, we don't care. We just say Nomad, hey, don't run that thing anymore. And so it's like we actually unwind the workflow. When we run the workflow, we'll be like, replicate the Docker container. So like if you're running like 2 data centers, for example, we basically take the container out of the staging registry and then we replicate it out to the remote data centers, and then we kind of go and do the scheduler thing, and then we talk to Vault and we do a bunch of other things. And then when we come to destroy those applications, we just do that in reverse, basically. And so clean up the periodic jobs is just us telling Nomad, don't run that thing anymore. So it works pretty well. Yeah, that's an interesting thing. So honestly, for the applications that we are, so our workload where this application is being used, or these series of applications are being used, they have a, so I'm just being careful because I can't talk about numbers. We haven't seen any problems at the scale we are and the traffic pattern we are at. If you have a different traffic pattern that is not so lumpy, then you might see a different behavior. So only because I don't have the experience. Like I heard that Lyft is running 2 million requests a second through it. So we are not doing that because our traffic pattern does not dictate that we do that. So we haven't seen any problems. But I guess that's all. I guess I can only tell you about our traffic pattern. That's a bit of a vague answer. I'm sorry about that. Any other questions? Yeah. That's a good question. So the question is how is the namespacing stuff actually implemented? So it's just a construct in Nelson. So Nelson's keeping that information inside its database. So from a runtime perspective, it's not like in Kubernetes, the namespaces that are over there that actually have a constraint. The analog here would be Nomad quotas, so our goal is to basically map those one-to-one so that we do actually have a quota for it, at least at the top level. So the root namespace for us ends up kind of being like a quota domain. So Nomad will have a concept of quotas, not released yet. But the concept of quotas is the idea, so that like if you're running a conversion infrastructure, you can might have like the foo quota and the bar quota, like can quota these sort of namespaces. But our namespaces are kind of completely like disjunct from that. It just so happens that the root namespaces will eventually map onto the quotas when that's made public. Yeah, right now it's a completely logical thing. There's nothing stopping you having a top level namespace that goes completely rogue and uses a lot of the cluster. We kind of manage that out of band right now. Mm-hmm. Any other questions? Anyone in the back? Okay, thanks very much, everyone.